Okay, thanks for the introduction. Good afternoon, everyone. I'm Yongqiang from Chinese Academy of Science. My topic today is on the construction of lightweight circulant involutory MDS matrices. And this is a joint work with Professor Mingsheng Wang. First, I'd also like to introduce some backgrounds. Linear diffusion layer is an important component in symmetric cryptography, as it provides internal dependency. It is, in fact, a linear mapping, which is aiming to maximize the number of active S boxes before and after it. Its performance is often measured by the branch number. And for a linear mapping X on n S boxes, each branch number is upbounded by n plus 1. And we know that every linear mapping can be represented by a matrix. Then for a linear mapping X on n S boxes, it is called an MDS matrix when its branch number achieves the upper bound. And for every MDS matrix, it can be represented by the following matrix, where in particular the entries Lij can be seen as M times M matrix over the finite fields with two elements. Here, where the M means the S box size. And also for lightweight cryptography, the implementation cost is also important. For linear mapping, it is called lightweight, means its implementation requires fewer XORs. In previous, there are two main construction methods for the construction of lightweight MDS matrix. The first one is the recursive constructions, which is usually based on linear feedback shift registers. By choosing suitable round functions, which is usually very light, and run it several rounds, one can get an MDS matrix. This construction always light, but it also leads to high latency since one has to run at least n rounds to get the output. The other main method, construction method, is the direct constructions, which is usually based on such as MDS codes over the finite fields. According to some recently research, one of them is given by the previous speaker. The choice of the MDS matrix over the finite fields, its entries should be choosing carefully because there are many factors that affect its implementation cost, such as the Hamming weight of the elements and also the choice of the irreducible polynomials. And in these two construction methods, there is one common feature. That is, the entries are always pairwise commutative. Or, for example, the multiplication with the elements from finite fields is always pairwise commutative. Or assumed to be pairwise commutative, such as the recursive construction. Here, the round function always chooses to be pairwise commutative. But we also like to ask a question: why always we using entries with pairwise commutative entries? And in my opinion, the most important advantage of using commutative entries is that it is very efficient to characterize whether a matrix is MDS or not. We know that a matrix is MDS if and only if every square submatrix are non-singular. When the entries are pairwise commutative, the determinants can be computed from the entries and then factorized into polynomials that the variables are the corresponding entries. And finally, one can get an equivalent set, condition set on how to choose the corresponding entries. But there are also some disadvantages of using commutative entries. One of the most is some interesting MDS matrix has been proved to not exist. And including the very interesting example that is the circulant involutory MDS matrix. It is circulant means it has a special structure, and then it is very easy to implant. And it is an involution means the same circuit can be used both in encryption and decryption circuit. Then, however, in 2009, the circulant involutory MDS matrix of order 4 is proven to do not exist. And last year, this result is generalized to that circulant involutory MDS matrix of any order also do not exist. In the same paper, they also proved that circulant orthogonal MDS matrix of order 2 to the D is also do not exist. But it should be remembered that these matrices do not exist over finite fields. And if you check their proof, you will find that their proof is only valid when the entries are commutative. But for the space of all linear, non-singular linear transformation, we know that it is non-commutative in fact. And the commutative part entries is only a small piece from the whole space. This also leads to another drawback, that is the restriction of using commutative entries may lose MDS matrix with fewer XORs. Based on these observations, we want to construct MDS matrix with non-commutative entries. And the first motivation is that we want to investigate whether it is possible to construct MDS matrix that has been proved to not exist when the entries are commutative. And we also want to give the lower bounds on XORs of some MDS matrix, and also give the constructions to achieve the corresponding bounds. And the method we used is, because we cannot compute the determinants right now, then we just compute the rank of all squares of matrix to determine whether a matrix is MDS or not. And for the lower bounds on XORs, we just search all possible entries and to determine it. Our methods restrict us to construct MDS matrix with bigger order, since it has to search too many entries. And in cryptography, 4x4 MDS matrix is usually often used. And the size of S boxes is often used of 4-bit or 8-bit. Then we focus on this size, n equals and m equals 4 or 8. And we also focus on this special matrix. Both circulant and Hadamard matrix can be defined by the row of the first entry. And both of them can be implanted easily. And we consider both of them in the case of involution and non-involution respectively. The last one is the optimal 4x4 MDS matrix. It is called optimal because it contains the highest number of entries with no XORs, and the fewest different entries for a 4x4 MDS matrix, which is only three different entries. And since one of our aim is to construct MDS matrix with as few as possible, with as few XORs as possible, then the entries with no XORs is preferred. But for the circulant and the Hadamard matrix, the number of entries with no XORs is limited by this general bound. For circulant matrix, the XORs of one row is larger than or equal to 2. This means that in one row of a circulant MDS matrix, it has at most 2 entries with no XORs. And for the Hadamard matrix, this bound is 3. And this means there are at most 1 entry with no XORs in one row of a Hadamard MDS matrix. Based on these observations, we suppose the entries in the first row and the first column is the identity matrix. This supposition will simplify our searching. Since most of our results are based on searching, before list our results, we give a trick which is used frequently in our searching process. That is using submatrix of order 2 to reduce the search space. We explain it with the example of circulant matrix with the first two rows entries are I, A, and B. And we know that it is MDS, then all its square submatrix of order 2 should be non-singular. Here is all the square submatrix of order 2. Then one of our aim is we want to transfer this matrix singularity with the entries itself. Then we have this result. And applying this result to all of the above submatrix, we can get a condition set. That is, if L is MDS, then the following matrix should be non-singular. And both A and B satisfies that the sum with the identity matrix should be non-singular. This can reduce the search space of A and B greatly. And for each candidate of A, the search space of B can be further reduced by using the other relations. We use this method on the laptop and with the software Magma. It takes nearly 3 days to verify that for a circulant matrix, if both A and B has XORs less than or equal to 1, then it cannot be a MDS matrix. This means if it is MDS matrix, then either A or B should have XOR larger than or equal to 2. Then we get the lower bound is 3. And the blue number here means that we found corresponding constructions achieve the lower bound when m equals 4 and equals 8 respectively. Next, we introduce the construction of circulant involutory MDS matrix. First, by the matrix multiplication, we can get equivalent conditions. From these conditions, we can see that the non-commutative is essential in these conditions because we can't cancel the A, C, and the CA. By using these conditions, we give a general construction. This construction also reduces the search space because the entries of B is computed from A and C, and the A and C are restricted to involution 2. Follow this construction, we will always get a circulant involution, and we only to test whether it is MDS or not. And the search method is similar as previous. And we run it on a laptop computer, and it takes nearly 1 week to get the following results. First is that the circulant involutory MDS matrix can be constructed with the method introduced. And when m equals 4, the lower bound on XORs of 1 row's entries is 5. And there are 48 constructions achieved, we found achieved the lower bound. And when m equals 8, we restrict XORs of A and C is less than or equal to 3. And under this condition, the fewest sum of XORs of 1 row's entries is 9. And we found 40,000 corresponding constructions. And we also construct a circulant involutory MDS matrix of order 5 because this type matrix is very interesting. And for both m equals 4 and 8, the XORs of 1 row's entries is m. Using the similar method, we also can construct a circulant orthogonal MDS matrix. As for the Hadamard involutory MDS matrix, it also can get an equivalent condition set for a Hadamard matrix to be involution. And From these conditions, we can see that if a Hadamard matrix with the first row's entry are I, A, B, and C, if it is an involution, then A, B, C should be pairwise commutative. We also like to point out that this condition is because one of the entries is the identity matrix. If we remove this supposition, the case will be different. And we also search it on a laptop computer. It takes nearly 1 day to get the result. When m equals 4, the lower bound on XORs of one row's entry is 6. And when m equals 8, the fewest XORs we get is 10. When the Hadamard matrix of non-involutory, the case of Hadamard matrix of non-involutory, it takes us nearly 4 weeks to get the following result. Most of the time is spent on the case of m equals 8. When m equals 4, the lower bound on XORs of one row's entry is 4. And when m equals 8, we consider the Hadamard matrix with this special type, where the first row's entries are I, A, transpose of A and B. For this special type, the lower bound on XORs of one row's entry is 5. Because it takes us much time to determine the lower bounds, and we do not try to find all MDS matrix achieved bound. We just search randomly and get almost 600 constructions achieved bound. At last is the optimal 4x4 MDS matrix. The lower bound on XORs of all its entries is 13 when m equals 4, and the lower bound is 10 when m equals 8. It is interesting that this matrix has fewer XORs in a bigger space. We also list some comparisons of our results. When m equals 8, the previous construction do not achieve the lower bound we get in the present paper, both in the non-involutory case and in the involutory case. And in the case of involutory, the circulant involutory MDS matrix has the fewest XORs. When m equals 4, only Hadamard involutory MDS matrix achieve the lower bound we found in the present paper. And we'd like to summarize the previous results on this slide. The first is that we construct a circulant involutory MDS matrix with non-commutative entries. And the second main result is that we give the lower bounds on XORs of one row's entry of some special MDS matrix. And in this table, the matrix red in the red color means that the corresponding lower bounds cannot be reduced because it has no conditions on the choice of the entries. But it should be remembered that at the beginning, in our construction, we suppose that the entries in the first row and the first column is the identity matrix. Then there is one more question, that is, if we remove the supposition, it's the lower bound of the previous table can be further improved. And the answer when m equals 4 is no. It takes us nearly 50 days searching, and to verify that for the case of circulant MDS matrix and the circulant involutory MDS matrix and the Hadamard involutory MDS matrix and the Hadamard MDS matrix, both these 4 cases, the lower bound on XORs cannot be further improved. At last, we would like to propose some problems that need further study. The first one is construct bigger order lightweight MDS matrix with non-commutative entries. And the second one is there are some other matrices that has been proved do not exist over the finite fields. For example, it has verified that circulant MDS matrix of order 8, when the elements choosing from the finite fields with 16 elements, it is not exist. Then it would be interesting to characterize the existence of 8 times 8 circulant MDS matrix, and the entries are choosing from the space of 4 times 4 non-singular matrix over the finite fields F2. There is also another problem, that is the circulant involutory MDS matrix of order larger than or equal to 6, whether they exist or not, especially the order of 8. And in essential, this problem is only one problem, that is how to characterize a matrix with non-commutative entries. Then how to characterize its singularity efficiently. Okay, that's all. Thank you.